thermal stresses and strains. Most of the materials expand or contract when they are heated or cooled. So if it is a heating process, the member gets elongated, and if it is cooled, there is a decrease in length. So this both conditions are free expansion. But if the expansion of a structural member is constrained, you can consider this case. Here I am subjecting this member to a temperature change, but at the same time both its ends are constrained. In this condition, what happens is there will be a stress developed in the body. So such type of stresses are called as thermal stresses. Consider a body like this. Initiate at temperature T1. When it is subjected to a temperature T2, the body gets elongated like this, and the change in length is given by delta LT. So T, why I am writing is because this change in length is due to the temperature change. To account for the temperature, I am writing it as delta LT. So this change in length is proportional to the temperature change. So what is this temperature change? T2 minus T1. At the same time, this change in length is also proportional to the initial length. So this is your initial length L. So combining these equations, I can write that the change in length delta L T is directly proportional to L into delta T. This change in length is equal to L delta T. To remove this proportionality constant, to remove this proportionality symbol, so this is your proportionality symbol. To remove the symbol, I am introducing a constant called as alpha. So this alpha is the coefficient of thermal expansion. So coefficient of thermal expansion alpha can be written as the change in length divided by original length to the change in temperature. So in the numerator, delta L by L is there, it won't have a unit, and in the denominator there is a temperature change, it will be having unit as degrees Celsius. So when you combine the numerator and denominator, you will be getting the final unit as 1 by degree Celsius or 1 by Kelvin. So the unit of the coefficient of thermal expansion is per degree Celsius or per Kelvin. So alpha may be a high value or alpha may be a low value. So what happens if alpha is high and what happens if alpha is low? So from the formula we can conclude alpha is equal to delta L by L divided by delta T. So this is your formula. So if your alpha is high, then it indicates that the elongation is high. So for the same delta T, if two bodies are considered, 1 and 2, a body with a higher coefficient of thermal expansion will have a larger change in length when compared to a body with a lower coefficient of thermal expansion. So a higher alpha means it will be having a delta L, a higher value compared to the delta L value of a material with a lower coefficient of thermal expansion. See, this will be elongating much, whereas this body 2 will be elongating by a small amount due to this coefficient of thermal expansion. Due to the thermal stress, there will be a thermal strain. So thermal strain can be calculated as change in length due to the temperature stress divided by the original length. So this delta L T is the change in length due to the temperature change, and the denominator L is the original or initial length. The thermal strain is denoted by the term epsilon T. You keep this equation as 1. So from equation 1, the change in length due to the thermal stress is equal to L into delta T into alpha. So now this thermal strain, this equation can be rewritten as L delta T alpha by L. So L gets cancelled. Finally, you will be having alpha into del T. So thermal strain is given by the product of coefficient of thermal expansion and temperature change. Thermal strain is given by the product of coefficient of thermal expansion and temperature change. thermal stresses in composite bars. If there are two bodies like this and one having a higher coefficient of thermal expansion and another one having a lower coefficient of thermal expansion. So if both of these bodies are subjected to a temperature change, this will expand by a length delta L, which is greater than the expansion of this body. You consider this as a body 1 and this is body 2. The expansion of this body, that is a change in length, is delta L1 and this is delta L2. If the body is having a higher coefficient of thermal expansion, then delta L1 will be more than delta L2, or the change in length of the body with a higher coefficient of thermal expansion will be more than the change of length in the body of lower coefficient of thermal expansion. But if there are bodies which are rigidly fixed like this, the two bodies are rigidly fixed like this, and if the bodies are subjected to a temperature change from T1 to T2, what happens is they expand as a common member and not as a separate one like this case. So we shall see a structural member. So this is a composite bar. This is made up of brass and steel. Brass will be having a higher coefficient of thermal expansion and steel will be having a lower coefficient of thermal expansion. So if the two bodies are not rigidly fixed, what happens is it is free to expand and brass will be moving from position Q to M, that is from here to here. From this position to this position Q to M, and steel will be expanding from Q to P. So these are the separate expansion shown in the red colored line. So till this point the brass expands and till this point the steel expands. But if the two bodies, brass and steel, are rigidly fixed, what happens is they will expand as a common member. So after expansion, both will stop at this point. So both will stop at the point P. So first we have to see what is free expansion. So free expansion is the expansion when the two bodies are not rigidly fixed, and actual expansion is the expansion when the bodies are fixed with each other. Now we have to calculate what is the actual expansion of steel. So the actual expansion of steel, that is from Q to P, how much it expands. So the actual expansion of steel is given by QP, sorry, the actual expansion of steel is given by Qn plus Np, because the actual expansion of steel is Q to P. So this I can consider as Qn plus Np. So what is Qn? Qn is the free expansion due to the thermal stress. So what is the formula for expansion when subjected to thermal stress? So that is given by L alpha delta T. Since you are taking the actual expansion of steel, you can write this as alpha S. Now Np. What is Np? So this is the elongation that is produced due to the pulling action of the due to the due to the pulling action of the brass. So I am having steel and this is a brass. So from N to P it elongates. So how this expansion is possible? So this expansion occurs because the brass is deforming and extending outwards. So this creates a tensile force in the steel body. Therefore, there will be a strain that happens due to the tensile force. So I can write Np as the strain, Np as the change in length due to tensile stress. So this is given by, so what is the change in length due to tensile stress? So this we have seen in the previous sessions. So the change in length is given by sigma by E into length. Since we are taking for steel, you can write SS. So this is your actual expansion of steel. Similarly, we can calculate for the brass, that is the actual expansion of brass is equal to, see, the actual expansion is from Q to P. So the actual expansion I can write from Q to P as Q to M minus PM. So what is Q to M? QM is the free expansion of the brass. So the free expansion due to the thermal stress is given by L alpha B into delta T. So this is QM. And what is PM? PM is a contraction that happens in the brass member. So when you see this, if both these bodies are connected together like this, what happens is a compressive force or compressive stress will be induced in this brass member. So what happens is, from here to here it is moving. So this is due to a compressive force. So now I have to take what is the change in length due to a compressive force. So the change in length due to a compressive stress is given by sigma by E into L. Since I am taking for brass, that is the stress is induced in the brass element, I am putting B and here also B. So this is the actual expansion of brass. You have to understand this concept clearly. See here the body is brass and at the bottom you are having steel. If they are separate or not rigidly fixed, what happens? There will be an elongation from Q to M, and similarly for steel the elongation will be from Q to N. But since both are rigidly fixed, they will be moving together and will end up at P. So this is the actual case. But in the free expansion process, it comes up to the point M. But in actual expansion, it is from Q to P. So this part has to go inside. So what happens is, in brass, a compressive stress is induced. Here in the case of steel, the free expansion is up to the point N, but in the actual case it goes up to the point P. So this part has to elongate like this. So this is possible only when a tensile stress acts on the steel member. So in the steel member, a tensile stress will be acting, and in the brass a compressive stress will be acting, or I can say a body with a higher coefficient of thermal expansion, so that will have compressive stress, and a body with a lower coefficient of thermal expansion will have a tensile stress. Also, for solving such type of problems, you have to use another one equation, that is the pull on steel is equal to the push on brass. Here I have used pull because it is a tensile stress in steel, and here I have used push because it is compressive stress in brass. Factor of safety. Factor of safety is defined as the ratio of ultimate load to the allowable load. In terms of stress, I can say factor of safety is equal to yield stress divided by allowable stress. In some fields of engineering, the term margin of safety is used. The margin of safety is equal to factor of safety minus 1. This factor of safety expresses how much stronger a system is than it needs to be for an intended load. Consider a structural member like this. This structural member is subjected to a load of 1000 kilonewton. So what happens if the load exceeds 1000 kilonewton? Even at 2000 kilonewton, the structure may withstand the force without breaking, but at some time what happens is the structural member may fail on the application of a force. So that load is called as the ultimate load. The load above which this ultimate load, the material will be failing. So if you draw the graph like this, which shows the force, your structural member will be subjected to a force within this limit. So this is your allowable load. But after this point, the member may fail. So this is your ultimate load. Okay, so after this point the material fails, and this is your point at which the force is acting for most of the time. So this is, you can think this as a design load also, design or service load. So most of the time the member will be subjected to this allowable load. So this factor of safety is the ratio of the ultimate load to the allowable load.